Exam review question related to chair conformations of cyclohexane. This is basically a continuation from part 1 and 2. In part A, we're awarded 9 points to appropriately draw the two chair conformations and their respective Newman projections. In part C, we need to calculate the difference between the two conformations in terms of energy, delta G. And in part D, we're asked to select the correct choice below and justify the selection in 10 or fewer words. Alright, let's get into it. So, just like I did in part 1, a lot of what goes into drawing chair conformations is arbitrary because at carbon 1, we have an isopropyl group projecting upwards, and it could be equatorial up or axial up. Just from experience, I know that at carbon 1 right here, we have an axial up substituent. So I can draw in axial up and classify this, just for now, as axial up. If at carbon 1 we have axial up, that means the axial substituents should alternate, just like the equatorial substituents we talked about in part 1. So if we have axial up here, we would have axial down at carbon 6. And if we continue, axial down, up, down. So if we have axial down at carbon 4, that means this methyl group is actually equatorial up. So already we have clues as to what could be the potentially more stable compound because we have two axial substituents and one equatorial. And following the chair flip, that would totally invert itself. These axial substituents would become equatorial and the equatorial will become axial. So at carbon 1, we have the isopropyl axial up. And at carbon 6, the OH group right here is axial down. At carbon 4, the equatorial methyl group will be projecting upwards. And now we can do the chair flip. At carbon 1 and 6, we have transaxial substituents, so following the chair flip, we should have trans-equatorial substituents at 1 and 6. At carbon 4, the methyl group, which is now in the equatorial position, will be an axial methyl group after the chair flip. Now drawing in the hydrogens is optional, but I feel like it will help us in the next part when we draw the Newman projection for both of these. So I didn't want to use a template here because I want you guys to sort of see where the Newman projection comes in. So even though 10 times out of 10 you'll be given a template on the exam, you should know where it comes from. So if we assume we're looking down carbon 1 and 6, as well as 3 and 4, the Newman projection should look sort of like this. So at carbon 1, we observe an axial up substituent, and at carbon 6, we have an axial down substituent. We have equatorial hydrogens. So that gives us a clue as to what the Newman projection looks like. Again, when we draw Newman projections for cyclohexane, it takes up the most stable conformation. So of course, all the substituents need to be staggered. So at carbon 1, we have an axial up substituent and equatorial substituents, and directly behind it, we have an axial down OH and equatorial substituents. So once we put in our two axial substituents, we can put in our hydrogens in yellow, and then we can connect this Newman projection with another one here to complete the entire cycle. Before we do that, we need to know that this is carbon 2 coming this way, and towards the back is carbon 6 leading to 5. Now, since this part of the cycle is projecting out at us, it will link up right here at the Newman projection, while at carbon 5, it will lead to carbon 4 and proceed towards the back of the Newman projection. That basically means the circle carbon right here in this Newman projection will be 4, whereas 3 will be the vertex. So from carbon 2, we lead to carbon 3, which has an axial up hydrogen and an equatorial down hydrogen, right here. And then directly behind it, we have an axial down hydrogen here, as well as an equatorial methyl, and the bond between 4 and 5. We have our equatorial up methyl group, and the hydrogen, which is projecting downwards, which is axial down. So remember, when we do a chair flip, our axial substituents become equatorial, and our equatorial substituents become axial. So if we look at our conformation again, our axial up isopropyl became equatorial up. Our axial down OH became equatorial down, and our methyl group, which was equatorial up, was then axial up at carbon 4. Taking that into account, all of our vertices will then have axial down instead of axial up here at 1 and 3. And then the cycle links up right here, axial down, and our equatorial substituents, followed by axial up here, and our equatorial substituent like so. And just like we did with the first Newman projection, we can fill in all of our substituents. At carbon 1, we have an equatorial up isopropyl, and at 6, the equatorial OH group. And then if we take a look at carbon 3, we have an axial down hydrogen, equatorial up hydrogen, and at carbon 4, an axial up methyl and an equatorial down hydrogen. We just do the direct translation like we did in the first conformation. So before we move on, let's just review. Carbon 1, axial up isopropyl. Carbon 6, axial down OH group. That's reflected here, axial up at 1, axial down at 6. And at carbon 4, we have an equatorial up methyl, which is attached to carbon 4 right here. In this conformation, we have trans-equatorial substituents, isopropyl up, and the OH down. That's reflected here. We have a methyl group projecting upwards, which is attached right here at carbon 4. So now in part C, we need to calculate the delta G, the difference in free energy between these two conformations that we drew in part B. The transition from axial to equatorial is a good transition because we reduce the potential energy of the compound and energy is released, so the sign associated there is negative. Any transition from axial to equatorial has a stabilizing effect. And if we go in the opposite direction from equatorial to axial, that has a less stabilizing effect in terms of that transition, and the delta G value will be positive in that case. So in order to fill out these numbers, just like we did in part A, we look at our substituents. At carbon 1 and 6, we had axial isopropyl and OH, which became equatorial, and our methyl group at carbon 4, which was equatorial, became axial up. So the transition of these two substituents will have a stabilizing effect, whereas the methyl group going from equatorial to axial will not. So that has a positive sign, whereas these two substituents will have negative signs. Solving for delta G1, we obtain negative 5.82 kilojoules per mole. And this number here that we got should make sense because when we transition from A to B, we have fewer axial substituents. So going from this compound to this one, in terms of conformation, will have a stabilizing effect. So because of that logic, the forward reaction is favored as opposed to the reverse. If we take a look at our two conformations, the one in which we have more equatorial substituents will be the favored conformation as opposed to this one. So K1, in theory, should be larger than K minus 1. In other words, the forward reaction is favored.